The Atlantic Ocean has an off switch, not a metaphor, a real one, made of nothing but salt and sinking water. In the layers of ice and seafloor mud, we can see that it has flipped before, and when it did, winters across the north changed within decades. It is on right now. It has been on for all of recorded history. This is the story of where that switch is, how it works, and what we actually know about how close it sits to the edge. First, proof the switch is doing something. Draw one straight line across a map of the Atlantic. On the eastern end, Lisbon, Paris, London. On the western end, at the very same latitude, the frozen coast of Labrador. Same distance from the sun, same tilt, same seasons. Yet a winter in Paris is mild, while a winter at that latitude in Canada can freeze the sea. Something is carrying heat from one side of the ocean to the other. That something is a river of warm, salty water riding north along the surface from the tropics toward Greenland, handing its heat to the air as it goes. By the far north it is cold, and salty, and heavy, so it sinks. It slides back south along the deep ocean floor, and the whole loop turns over, again and again. The scale is hard to hold in your head. 17 Sverdrups of water, more than 10 times the flow of every river on Earth combined. 1.25 petawatts of heat moving north, roughly 1 million large power stations running flat out, and all of it hangs on one quiet act: water sinking at the top of the world. Stop the sinking, and you have found the switch, so everything hangs on sinking. Let me redraw that loop as something simpler. Forget the map. Picture two great tanks of water joined in a ring. The warm branch carrying water one way along the top, the cold branch carrying it back along the bottom. A loop, a circuit. And like any circuit, what matters is the valve. The valve here is the place in the north where surface water sinks. Hold that valve open, and water pours down into the deep, and the whole loop runs strong. Let it close, and the circulation stalls. So what decides whether the water sinks? One thing only: density. Heavier water sinks beneath lighter water, always. And the density of seawater is set by just two things: its temperature and its saltiness. Cold water is denser than warm. Salty water is denser than fresh. Up in the north, the surface is both cold and salty, so it is heavy enough to fall, and the valve stays open. Hold on to that, because it is the whole story. This loop is not driven by some giant hidden engine. It is driven by the plain fact that water in the north is dense enough to sink. Temperature, we cannot do much about, but salt is a lever, and a lever wired into a loop is where this story turns strange. Here is where it gets interesting, because salt does not just sit there. It rides the current, and that creates a loop inside the loop. Follow it around. The warm surface branch climbs up from the tropics, where the sun has baked it salty. It carries that salt north. Salty water in the north is dense, so it sinks readily, which keeps the current strong, which drags even more salt north. Strong begets salty, and salty begets strong, a feedback that holds itself up. But every reinforcing loop can run the other way. So now add fresh water at the top. Rain, rivers, ice melting off Greenland. The surface there turns less salty. Less salty is less dense, so less of it sinks. The current weakens. A weaker current carries less salt north, which leaves the north fresher still, which weakens it further. The very same loop that held the circulation up can drag it down. That is the engine of the whole problem, and it is why this system does not simply dial smoothly up and down. In 1961, an oceanographer named Henry Stommel wrote this feedback down as a simple model. Two boxes of water, the tropics and the north, joined by a single flow, and he found something that surprised people. For the very same conditions, the same sun, the same winds, his equations gave not one answer but two equilibria, sitting in the same system at the same time. In the first, the current runs strong, salt keeps streaming north, and the loop stays on. In the second, fresh water has won, the sinking has stopped, and the loop sits quietly off. Both are stable, both can last for centuries. Nudge the on state a little, and it springs back to on. Nudge the off state, and it settles back to off. Now, you might think a sketch this small proves nothing about a real ocean, but the same two states keep showing up in far bigger models, the ones that simulate the whole planet, ocean and atmosphere together. That is what made people take a pair of boxes seriously. A system with two stable states for one set of conditions has a name. We call it bistable. A light switch is bistable, And so it seems is the Atlantic, which changes the whole question. We stop asking how much the current will slow. We start asking which of its two states it will end up in. But if there are two states, here is the unsettling part. Getting from one to the other is not a road you can simply walk back. Picture a slow dial that adds fresh water to the north. Turn it up gently. For a long time, almost nothing happens. The current holds and holds and holds. The feedback is propping it up. Then you cross one last step, and the system jumps. The sinking fails and the loop drops to off, all at once. Now try to undo it. Turn the fresh water back down to where the current was still running happily. It does not switch back on. To restart the loop, you have to remove far more fresh water than the little bit that tipped it. The path down and the path back are different paths. This is called hysteresis, and it is the fingerprint of a tipping point. It means a system can hold steady right up to an edge, give almost no warning, and then settle into a new state it will not easily leave. Almost no warning, but not quite none. Near an edge like this, the mathematics leaves one faint fingerprint. Kick the system and watch how quickly it recovers. Far from the edge, the pull back to normal is strong, and the recovery is quick. Close to the edge, that pull goes slack. The same small kick takes longer and longer to fade away. Scientists call this critical slowing down, a system whispering that its grip is loosening before anything visibly breaks, which is why what we actually measure matters so much. So, the question from the very beginning, how close is the edge? Honestly, no one knows for certain, and that is the truth of it. What we do have is measurement. Since 2004, a line of instruments strung clear across the Atlantic, the Rapid Array, has watched the current directly. The record is short, only about 2 decades, but it is real, and it shows a circulation that is variable, and that may have weakened. And we can read the past, those layers of ice and seafloor mud from the start of this story. In them we find times when this circulation changed fast, within decades, and northern climates lurched along with it. The system has done this before. Here is the careful version, the one the evidence actually supports. The current is very likely to weaken this century as the north warms and ice melts. A full collapse before the year 2100 is not expected, but it cannot be ruled out. That is not a forecast of disaster. It is an honest measure of how much we still do not know about a switch we would very much like to keep in the on position. Step back from the ocean for a moment. What you have really been looking at is a shape, a system with a reinforcing loop buried inside it, 2 stable states, and a path between them that refuses to retrace itself. Once you know that shape, you begin to see it everywhere. A clear lake that tips, in a single season, into a murky green one, and will not easily clear. A grassland that flips to desert and stays put. Even the light switch on your wall, holding its position until you push it past the middle. Different systems, the same skeleton. The Atlantic is simply the grandest example we live inside. A river of warm water held up by its own salt, carrying heat to half a continent, resting in one of its 2 possible states. It has been on for all of recorded history. So the question we are left with is not whether it works. It is how hard we want to lean on a switch when we are not quite sure where the middle is.